Okay. Now you know the noise analysis of analog modulation technique, AM, FM, PM, what is figure of merit and everything. Okay. Now we'll solve a few problems of this noise analysis of analog communication. Now classroom workbook problems. Okay. Now the classroom workbook problem, question number 1. Okay. What is the question number 1? Now question number 1 is a message signal band limited to a message signal band limited to 15 kHz and is transmitted through a channel after modulation. And it is transmitted through a channel after modulation. And it is transmitted through a channel after modulation. The channel is affected by additive white Gaussian noise. The channel is affected by additive white Gaussian noise, whose two-sided power spectral density, double-sided power spectral density is N0 by 2, which is 10 power minus 10 watts per Hz, wideband noise. And the power loss in the channel is, the power loss, this is additive white Gaussian noise is affected. The power loss in the channel is 50 dB. The power loss in the channel is 50 dB. The power loss in the channel is 50 dB. The signal to noise ratio, and it is going for receiver, demodulation process, receiver. And the signal to noise ratio at the output of the receiver is, signal to noise ratio at the output of the receiver is 40 dB. Sorry, signal to noise ratio at the output of the receiver is 40 dB, right? 40 dB. So this dBs we converted into magnitudes. Therefore, this is 10 power 5, and this is signal to noise ratio at the output of the receiver in terms of magnitude is 10 log, 10 cancel. So which is nothing but apply until other than 10 power 4. Okay. So this is the given data. Okay. But what he is asking? What he is asking? See, this is a message signal band limited to 15 kHz is transmitted to a channel after modulation affected by additive white Gaussian noise with a power loss of 50 dB, and the signal to noise ratio at the output of the receiver is 40 dB. Okay. So now the question what he is asking is calculate the transmitted power, calculate the transmitter power, or calculate the output power of the transmitter. Now this is the output power of the transmitter. He is asking calculate the transmitted power. Okay. Now this is the receiver, this is input signal to the receiver, and this is the output signal. Now you see here, what is the signal power? The signal power at the input of the receiver is nothing but the total transmitted power. The signal power at the input of the receiver is nothing but the total transmitted power minus losses. So if the power loss is 0, whatever the transmitted power, that should be the signal power, right? Now if a power loss is 0, whatever the signal power at the input of the receiver will be the total transmitted power. Okay, without loss. This is in terms of dB. So from here, the total transmitted power, which is nothing but signal power plus losses. So this is in terms of dB. Now I want in terms of magnitude. So the total transmitted power, which is nothing but signal power multiplied with power losses. That is the total calculate the output power of the transmitter required for a different modulation index. Different modulation technique. This is the question for a different modulation technique. First, what he is asking is, now the modulation is DSB-SC. DSB-SC modulation. So, DSB-SC modulation. So, what happens if DSB-SC modulation? So, how to solve that? So, here SI is not available. So, we want to find SI. For that, which parameter is useful? Figure of merit. What is the figure of merit of DSB-SC? 1. Signal to noise ratio at the output of the receiver, which is equal to signal to noise ratio at the input of the receiver, right? Now see here. Now, signal to noise ratio at the output of the receiver is given as how much? 10 power 4. Now, SI, what is SI? 10 power 4 into NI. You know what is NI? NI is a noise power due to the message signal bandwidth. Okay. Now that also you calculate. What is NI? NI is also common. Now NI, which is nothing but N0 into omega. So NI, which is equal to N0, is 2 into 10 power minus 10 into omega 15 kilo. So therefore NI, which is equal to 2 into 15, 30 into 10 power minus 10 into 10 power 3. So what is NI? NI, which is equal to 3 into 10 power minus 3, 4, 10 power 4, 10 power minus 6. This is NI fixed. So now here, which modulation? DSB-SC modulation. So SI, which is equal to 10 power 4 into NI. NI is 3 into 10 power minus 6. Therefore, SI, which is equal to 3 into 10 power minus 2. Now, what is the total transmitted power? The total transmitted power, which is equal to SI is 3 into 10 power minus 2. Now, into power loss. Power loss is 10 power 5. So, this is the total transmitted power, which is equal to 3 kilowatt. Now, this is the DSB-SC signal. Now, SSB-SC signal. Now, the next one is, both are same, SSB or DSB is same. Next one is AM. AM with modulation index equal to 1. AM with modulation index equal to 1. Now, what is the figure of merit? Figure of merit is mu square by 2 plus mu square. Therefore, figure of merit is 1 by 3. Now, what is the figure of merit? Signal to noise ratio at the output of the receiver, which is equal to 1 by 3 into signal to noise ratio at the input of the receiver. Now, which is nothing but SI by NI, which is equal to 3 into S0 by N0. So, SI by NI, which is equal to 3 into S0 by N0. What is S0 by N0? 10 power 4. Now, SI, which is equal to 3 into 10 power 4 into NI. Therefore, SI, which is equal to 3 into 10 power 4 into NI is 3 into 10 power minus 6. Therefore, SI, which is equal to 3 into 3, 9 into 10 power minus 2. So now the total transmitted power which is equal to 9 into 10 power minus 2 into the power loss. The power loss is 10 power 5. So the total transmitted power which is equal to 9 kilowatt. Right? AM requires more power because carrier upper sideband, lower sideband. But DSBS is only total power equal to only sideband power. Okay. Carrier is suppressed. Now, FM with modulation index beta equal to 5. Figure of merit which is equal to 3 by 2 into beta square which is equal to 3 by 2 into 25 which is equal to 75 by 2. So signal to noise ratio at the output which is equal to 75 by 2 into signal to noise ratio at the input. Now which is equal to SI which is equal to 2 by 75 into S0 by N0. Now which is equal to SI which is equal to 2 by 75 into S0 by N0 which is 10 power 4. So now the total transmitted power which is equal to 2 by 75 into 10 power 4 into SI by NI. Now which is equal to NI which is equal to 2 by 75 into 10 power 4 into NI. What is NI? NI is nothing but 3 into 10 power minus 6 which is equal to 2 into 3 by 25 into 3 into 10 power minus 2 which is equal to 3 cancel 2 by 25 into 10 power minus 2. Therefore, what is the total power? Total power is nothing but SI 2 by 25 into 10 power minus 2 into power loss. What is the power loss? Power loss which is 10 power 5 which is equal to 2 into 10 cube by 25. Now which is equal to 80 watts. Now here also you can easily understand FM requires less power. AM requires more power because here the information is in terms of amplitude, but here the information is not in terms of amplitude. Envelope is constant. Unmodulated carrier power, the total transmitted power will be same as that of unmodulated carrier power. Like that the questions are asking. This is question number 1 in our classroom workbook problem. Okay. Now this is the, if you understand the noise analysis, then this question is very easy, right? Right, now we'll see classroom workbook question number 2. Now this is question number 2. What is question number 2? Now we'll see. Now a video signal, a 1 milliwatt video signal, means here power is given. A 1 milliwatt video signal. Which signal? Video signal. A 1 milliwatt video signal having a bandwidth of, yes, because video signal is having highest. A video signal is having a bandwidth of 100 MHz, is transmitted to the receiver through a cable, has a loss of, power loss is given, cable loss is given, which is 40 dB. Therefore, in terms of magnitude, this is 10 power 4. And the cable is affected by noise. One-sided power spectral density. What is the one-sided power spectral density? One-sided power spectral density means only N0. One-sided power spectral density is N0, which is equal to 10 power minus 20 watts per Hz. Then what he is asking is, he is asking signal to noise ratio at the input of the receiver. What he is asking is, he is asking the signal to noise ratio at the input of the receiver here. He is asking what is the signal to noise ratio at the input of the receiver. Okay. So he is not giving all these things. This is the given data. Once again, see. Okay. I just explain the question once again. A 1 milliwatt video signal having a bandwidth of 100 MHz is transmitted through a cable having a loss of 40 dB. Now, whose noise affected is one-sided is 10 power minus 20. And what is the signal to noise ratio at the input of the receiver is the question. So, SI, what is SI here? Now, from here we can SI, which is nothing but total transmitted power by losses. So the transmitted power is already given, 1 milliwatt by losses is 10 power 4, which is equal to 10 power minus 3 by 10 power 4, which is equal to 10 power minus 7. Okay. Now, Ni, I want Ni. What is Ni? Ni is nothing but N0 into omega. N0 is given 10 power minus 20 watts per Hz. Omega is 100 MHz, 10 power 6, which is equal to 10 power minus 20 into 10 power 8, which is equal to 10 power minus 12. Clear? Now, signal to noise ratio at the input of the receiver is SI by Ni, 10 power minus 7 by 10 power minus 12, which is equal to 10 power 5. And the signal to noise ratio at the input of the receiver in terms of dB, which is equal to 10 log 10 power 5 base 10, which is nothing but 50 dB. Now down. Question number 3. The AM signal represented in time domain as S of t of AM, which is given as 10 into 1 plus 0.5 sin 2 pi Fm into t into cos 2 pi Fct. This is an AM signal represented in time domain. Okay. So the AM signal represented in time domain as this. Now it gets added to a noise with a power spectral density, a noise whose power spectral density is as shown in the figure below. This is a noise whose power spectral density is given as power spectral density is given to you. Now this is the noise power spectral density which is given to you, right? Now see here, an AM signal represented in time domain and it gets added with a noise power spectral density is given, and what he is asking is what is the ratio of sideband power to the noise power. Okay, what is asking? Ratio of sideband power to the noise power. Now what is an AM signal in time domain? Now this is the AM signal AC into 1 plus mu cos 2 pi Fm into t into cos 2 pi Fct. Now this is an AM signal represented in time domain. AC which is equal to 10 volts, modulation index which is equal to 0.5. What is the sideband power? The sideband power which is equal to Pc into mu square by 2. So the sideband power Pc is nothing but AC square by 2R into mu square by 2. So the sideband power which is equal to AC square 10 into 10 by 2 into 1 ohm into mu is 0.5 whole square by 2, which is equal to the sideband power which is equal to 25 by 4. This is the sideband power. Now noise power, but this is noise power spectral density. You know that the noise power spectral density, the noise power which is equal to area under power spectral density. Is it right or not? Area under noise power spectral density is nothing but noise power. What is integration? Integration is nothing but area. Now can you find the area here? Now yes, this is a triangle. So half base is B, height is n0 by 2. So how many are there between minus infinity to plus infinity? Now this is 4 are there. So multiplied with 4. So which is nothing but 4 cancel n0 B. But what he is asking? He is asking to find the sideband power to the sideband power to the noise power. The sideband power to the noise power which is 25 by 4 n0 B. This is the sideband power to the noise power. Note down. Right, now question number 4. Now this is question number 4. Now by considering the system as shown in the figure below, now this is the system which is given to you. M of t cos omega naught into t. M of t into cos omega naught into t, and this is a multiplier cos of omega naught t plus theta, and this is passed through a low pass filter. It is passed through an ideal low pass filter having a gain of 1, and here omega naught ideal low pass filter, cutoff frequency is FM. Cutoff frequency is FM, and is mentioned omega naught is greater than FM. And this is the output. Now what he is asking is, he is asking power here, power at the output signal, power of the output signal. This is the question what he is asking. Okay, now first we will see what should be the output signal, then after that we will find the power. So now this is a multiplier. Now what is the output of the multiplier? The output of multiplier is nothing but m of t into cos omega naught t plus theta into cos omega naught into t divided with 2 multiplied with 2 cos a cos b. Now which is nothing but m of t by 2 cos a cos b cos of a plus b. Cos of a plus b means 2 omega naught t plus theta cos of a minus b, m of t by 2 cos of a plus b plus cos of a minus b cos theta. And it is passed through a low pass filter. Low pass filter frequency is, cutoff frequency is FM, but omega naught is 2 pi FM into 2 FM, which is not allowed. So what is the output signal finally? Now this is the output signal. Now the output signal is, let us assume this is some x of t. The output signal x of t, which is equal to m of t by 2 into cos theta. Then I want the power of the output signal. Power of the output signal, which is nothing but expectation of x square of t, which is nothing but expectation of m square of t by 4 into cos square theta. So see here, 1 by 4 into cos square theta, and in the question is already mentioned a power of the message signal is mentioned a message signal m of t. The question is mentioned a message signal m of t band limited to FM, and a power of the message signal is PM is mentioned. A message signal is having a band limiting frequency of FM, a message signal has a power of PM. So yes, this is the power of the message signal, which is nothing but expectation of m square of t, now which is nothing but 1 by 4 into cos square theta into PM. Okay, now this is question number 4. So this is a noise analysis of analog modulation technique, and we'll solve some problems, okay, in the next session.